Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. We will be talking on the module, the vibrating diatomic molecule as simple harmonic oscillator under the paper Atomic, Molecular and Laser Spectroscopy. After completing it, we'll be able to learn about the simple harmonic oscillator, energy levels, spectrum, population of energy levels. Simple harmonic oscillator and how to calculate the frequency of vibration. It is assumed that the atoms of diatomic molecule are vibrating along the direction of the bond, due to which there is a periodic lengthening and shortening of bond length. Thus, a vibrating diatomic molecule can be approximated to a linear harmonic oscillator, whose frequency of vibration can be calculated using Newton's equation of motion. Let the two atoms of the molecule with masses m1 and m2 are joined with a string having spring constant k. As there is no external force, there is no effect on the center of mass due to oscillations of the atom. The two atoms vibrate back and forth with respect to center of mass. According to Hooke's law, force exerted by the two atoms of a molecule on each other when these are displayed from equilibrium position is proportional to the change in the internuclear distance. Now suppose the bond distorted from its equilibrium length Re to a new length R, then restoring force on each atom of diatomic molecule R. m1 d2 r1 by dt square is equal to minus k r minus Re, and m2 d2 r2 upon dt square is equal to minus k r minus Re, where k is known as force constant and is measure of the stiffness of the bond. R1 and R2 are the positions of atom 1 and atom 2 with respect to center of mass of the molecule. And we know that R1 is equal to m2r by m1 plus m2 and R2 is equal to m1r by m1 plus m2. Putting the value of R1 in the first equation of motion, one gets m1 m2 divided by m1 plus m2 d2r by dt square is equal to minus k r minus Re. Since Re is constant, its differentiation with respect to t will be 0. So, d2r by dt square is equal to d2r minus Re by dt square. Putting in equation 1, m1 m2 by m1 plus m2 d2r minus Re by dt square is equal to minus k r minus Re. And now taking r minus Re is equal to x and writing m1 m2 by m1 plus m2 is equal to m, where x represents the displacement of the bond length from its equilibrium position. So the equation 2 can be written as m prime d2x upon dt square is equal to minus kx, or d2x by dt square plus k upon mx is equal to 0, and d2x upon dt square plus omega square x is equal to 0, where we have replaced k by m by omega square. This is the equation of simple harmonic motion with frequency of vibration, and the units are centimeter inverse. So the frequency of vibration is equal to 1 by c k by m under the root, which is further equal to 1 by 2 pi c k by m prime under the root. Energy levels. Vibrational energies, like other molecular energies, are quantized, and the permitted vibrational energies for any particular system can be calculated from Schrodinger equation. The eigenvalues for the energy of a linear harmonic oscillator are of the type E nu is equal to nu plus 1 by 2 h cross c omega, where nu is the vibrational quantum number equal to 0 or an integer, and omega is the vibrational frequency of the oscillator expressed in wave numbers. We shall now derive it using Schrodinger wave equation. A vibrating diatomic molecule is approximated as a harmonic oscillator. The potential energy function under the influence of which nuclei vibrate is then parabolic and is of the form given by Vr is equal to 1 by 2 k r minus Re square is equal to half k x square, where x is the displacement from the mean position or the equilibrium position. Then the Schrodinger equation can be written as d2 psi upon dx square plus 8 pi square m upon h square ev minus half kx square psi is equal to 0, where m prime is the reduced mass of the atomic molecule. If we put alpha is equal to 8 pi square m prime e nu upon h square and beta is equal to 4 pi square m prime k upon h square under the root equal to 2 pi m prime k upon h square under the root, then d2 psi upon dx square plus alpha minus beta square x square psi is equal to 0. And we introduce a dimensionless independent variable xi is equal to beta under the root dot chi, so that d2 upon dx square is equal to beta d2 upon d xi square. In previous equation, this beta d2 psi upon d xi square plus alpha minus beta square xi square upon beta psi is equal to 0, or d2 psi upon d xi square plus alpha by beta minus xi square into psi is equal to 0. And if we try a solution of this equation in the form psi xi is equal to c u xi e raised to the power minus xi square upon 2, then equation on putting for the value of psi and d2 psi upon d xi square becomes d2 u upon d xi square minus 2 xi du upon d xi plus alpha by beta minus 1 u is equal to 0. This will become Hermite differential equation provided we put alpha by beta minus 1 is equal to 2 nu or alpha by beta is equal to 2 nu plus 1, so that we can replace u xi by Hermite polynomial h nu xi. Thus, d2 h nu xi upon d xi square minus 2 xi d h nu xi upon d xi plus 2 nu h nu xi is equal to 0. Therefore, solution of Schrodinger equation becomes psi is equal to c h nu xi e raised to the power minus xi square upon 2, and is valid only for the values of nu 0, 1, 2 and so on. The restriction on nu also restricts energy values E. Finally, writing alpha by beta is equal to 2 nu plus 1 and writing alpha and beta values 8 pi square m prime e nu upon h square upon 2 pi m prime k upon h square under the root is equal to 2 nu plus 1, which is equal to 2 can be taken common out, nu plus 1 by 2 omega. So, E nu is equal to h upon 2 pi k upon m prime under the root nu plus 1 by 2, so that it is equal to h nu plus 1 by 2, so that hc omega is equal to nu plus 1 by 2, where omega is the vibrational frequency of the vibrating diatomic molecule expressed in wave number. This equation gives the allowed energies for the harmonic oscillator. Significance of this equation lies in predicting the existence of 0 point energy equal to half hc omega nu is equal to 0. If we transform energy value to term value on dividing by hc, we obtain for vibration terms g nu is equal to E nu upon hc is equal to omega nu plus 1 by 2. So, putting the value of nu is equal to 0, 1, 2 and so on, we get g nu is equal to omega by 2, 3 by 2 omega, 5 by 2 omega and so on. Thus, we have a series of equispaced discrete vibrational levels as has been shown in the figure, the common separation being omega centimeter inverse. The spacing between vibrational levels is considerably larger than the spacing between rotational levels of a molecule. If we talk about the spectrum, suppose a transition occurs from a upper vibration level in which the quantum number is nu prime to a lower state with quantum number nu double prime. The change in vibrational energy will be E nu prime minus E nu double prime is equal to nu prime minus nu double prime hc omega. The frequency nu of the radiation in wave numbers accompanying the vibrational transition would be nu is equal to E nu prime minus E nu double prime upon Hc is equal to nu prime minus nu double prime omega, which is equal to G nu double prime minus G nu prime. Suppose a transition occurs between nu prime is equal to 1 and nu double prime is equal to 0, then delta E 10 is equal to E10 minus E0 double prime is equal to Hc omega. The frequency of this transition will be nu at T0 is equal to delta E upon Hc at 10 is equal to omega centimeter inverse, which is further equal to 1 by 2 pi c k upon m prime centimeter inverse. Therefore, one can write delta E10 is equal to Hc nu 10. Thus, vibrational spectrum is expected to consist of a single band at omega centimeter inverse. Thus, an intense band in infrared spectrum is to be concluded as vibrational spectrum, owing its origin to harmonic vibrations of the nuclei along internuclear axis. However, infrared spectrum also consists some weak bands, and these are referred to as overtones at frequencies slightly lesser than 2 omega, 3 omega, and so on. Their appearance suggests that vibrations deviate from being harmonic, and analysis should be made by treating the vibrating diatomic molecule as an anharmonic oscillator. The vibrational spectra are known only in absorption. Electromagnetic radiations can induce transitions among the vibrating molecule. An electrical coupling must be present. If the vibrating molecule produces an oscillating dipole moment, then the desired coupling results due to the interaction of this dipole moment with electric field of the radiation. Consequently, homonuclear diatomic molecules like H2, N2 and O2 that possesses a zero dipole moment for any band length will not interact with the radiation. On the other hand, molecules like HF, HCl, HBr, HCN have a dipole moment that is some function of internuclear distance, and consequently gives rise to an oscillating dipole moment, will exhibit the vibrational spectra. Population of energy levels. Considering the case of HCl molecule, it is the simplest molecule we consider, where the frequency of spectral line arising due to transition between 0 is equal to 0 and nu is equal to 1 states is nu 102890 centimeter inverse. So that delta E10 is equal to Hc nu 10. We know the values of H, C and nu. H is 6.62 into 10 is power minus 27, C is 3 into 10 is power 10, and nu has been given out to be 2890. So, calculating it, 5.75 into 10 is power minus 13 arc. Representing the energy of a molecule in nu is equal to 0 state, the lowest state is much greater than the population N1 in nu is equal to 1 state, or in other words, only a large small fraction of the molecules populate the vibrational levels at ordinary temperature. This means that most of the molecules are in the lowest allowed vibrational state. In a spectroscopic study, therefore, one investigates the absorption of radiation by these R is equal to 0 states molecules. Thus, main vibrational transition in absorption is nu is equal to 0 to nu is equal to 1. There are certain transition rules. For the probability of any given transition, it is essential to assume that the diatomic molecule has a permanent dipole moment. For a linear harmonic oscillator, the eigenfunctions are of the form psi n is equal to nn e raised to the power minus q square by 2 h n q, where Q is equal to x under the root b, in which this x is displacement of the particle from the equilibrium and b is equal to 4 pi square nu m upon h. Nu is the frequency of oscillation of the particle of the mass m, Nn is the normalizing factor, and h and q represents a Hermite polynomial of degree n, and this Hermite polynomial is defined as h and q is equal to minus 1 raised to the power n e raised to the power q square dn e raised to the power minus q square upon dqn. By inserting the appropriate eigenfunction in the equation, p mn x is equal to integration of psi m star mu x psi n d tau. We find that the result differs from 0 only if the change in the vibrational quantum number in the two states between which transition is to occur is equal to unity. Therefore, for a harmonic oscillator, selection rule is delta nu is equal to plus minus 1. Putting this condition in equation 3, nu is equal to omega, predicting that for a harmonic oscillator the frequency V nu of the radiation emitted or absorbed should be equal to the mechanical frequency omega of vibration of the system. Thus we find that the classical theory, quantum mechanically the frequency of radiated light is equal to the frequency nu of the oscillator, no matter what the nu value of the initial state is. The figure shows that the allowed transitions are indicated by vertical lines, and it is obvious from the figure that they all have given rise to same frequency. There are some assignments to understand the concept. Again, considering the simplest molecule of HCl, which has a single intense band at 2882.9 centimeter inverse in the near infrared spectrum. If this is a vibration spectrum, find out the vibrational frequency. So it's quite simple that nu is oscillatory is equal to omega c is equal to 2885.9 into 2.9979 into 10 to the power 10. So comes out to be 8.65 into 10 to the power 13 hertz. Further, find the force constant for the HCl bond if the vibrational frequency of HCl is 8.9 into 10 to the power 13 Hz, where HCl can here be written as H1 and C in chloride 35. Also calculate the reduced mass of the molecule. So the reduced mass, let us first calculate as mu is equal to m1 m2 by m1 plus m2. So putting the values of mass of hydrogen, mass of chlorine, and calculating it, 1.6261 into 10 to the power minus 27 kilogram. M1 being the mass of the hydrogen and M2 that of the chloride. So nu oscillatory is again 8.97 into 10 to the power 13 hertz. It has been given to us is equal to 1 by 2 pi k upon nu under the root, which is equal to 1 by 2 into putting the value of pi 3.14 and k upon writing the value of this mu as 1.6261 into 10 to the power minus 27 kilogram, so that k can be calculated from this, and it comes out to be 516 Newton per meter. If the fundamental vibrational frequency of HCl given to be 2990 centimeter inverse, calculate the fundamental frequency of DCl molecule assuming same force constant. Now we know the relation omega is equal to nu oscillatory upon c is equal to 1 by 2 pi c k upon mu under the root. So dividing omega DCl upon omega HCl is equal to omega DCl upon writing the vibrational frequency of HCl as 2990 centimeter inverse is equal to mu HCl upon mu DCl under the root is equal to mass of deuterium plus mass of chlorine into mass of hydrogen divided by mass of hydrogen plus mass of chlorine into MD, mass of deuterium, is equal to 2 plus 35 into 1 upon 1 plus 35 into 2 the value comes out to be 0.5139 under the root. So omega DCl upon 2990 is equal to 0.71687. So omega DCl can be calculated and it comes out to be 2143.4 centimeter inverse. Atomic weight of each atom of the chlorine molecule is 35. The fundamental vibrational band of the molecule is at 2940.8 centimeter inverse. Find out the corresponding fundamental vibrational band chlorine molecule in which one atom has atomic weight 35 and the other has 37. It is quite interesting. Further, to find out the separation of the spectral lines. So again the relationship is omega is equal to nu oscillatory upon C is equal to 1 by 2 pi C K upon omega mu reduced mass under the root. So omega Cl35 minus Cl35 chlorine molecule is equal to 1 by 2 pi C K upon mu of chlorine molecule under the root, which is given to be 2940.8 centimeter inverse. So putting this in this equation, 2940.8 divided by omega Cl35 my Cl37 is equal to mu Cl37 upon mu Cl35 under the root is equal to 70 into 37 upon 35 into 72 under the root. This comes out to be 1.01379. So that one can calculate the vibration frequency of this chlorine whose atomic weight is 35 and the other is 37, comes out to be 2900.8 centimeter inverse. Therefore, the separation of the spectral lines is 40 centimeter inverse. If we see that that of the chlorine, which was given to be 2940.8 centimeter inverse, and while that of the we have calculated where the atomic weight was different as 35 and 37, it is 2900.8 centimeter, and making the difference comes out to be 40 centimeter inverse. Calculate the ratio of the number of molecules in nu is equal to 1 to nu is equal to 0 vibrational state at 298 Kelvin if the spacing between the levels is given to be 2 into 10 to the power minus 13 arc per mole. So the number of molecules n nu in the new vibrational state with respect to nu is equal to 0 is given by the relationship n nu is equal to 1 upon n nu is equal to 0 is equal to E cross P minus G nu, where nu is 0, Sc upon kBt. So that we can write down n1 upon n0 is equal to exponential, writing the value of this spacing given to be 2 into 10 to the power minus 13 divided by 1.38 into 10 to the power minus 16 arc per degree per mole into 298 is equal to exponential minus 4.86334, and the value comes out to be nearly 0.008, which is less than 1% of the molecules are in the nu is equal to 1 state. For HCl molecule, the separation between adjacent vibrational states is 2885.9 centimeter inverse. Calculate the ratio of the number of molecules in nu is equal to 1 to nu is equal to 0 vibrational states at 1000 Kelvin. So again the formula remains the same, n nu is equal to 1 upon n nu is equal to 0 is equal to exponential minus G 0 nu Sc upon kBt. Putting all the values of, we know the value of G naught, we know the value of H, we know the value of C, and Kb also known to us, and temperature here given to be 1000 Kelvin. So calculating it, we get 9.72 into 10 to the power minus 7. What will be the ratio of HCl molecules in the first excited rotational state in those in the first excited vibrational state at 1000 K? The rotational constant is given to be 1.32 into 10 to the power minus 3 electron volt, while the separation between adjacent vibration levels is 2990 centimeter inverse. Using the value of Nj is equal to 2j plus 1, N0 exponential minus Ej upon kBt, and N nu is equal to 1 to N nu is equal to 0 is equal to exponential minus G 0 nu Sc upon kBt. So writing Nj is equal to 1 upon N nu is equal to 1 gives us you thrice times exponential minus Ej is equal to 1 upon kBt upon exponential minus E nu is equal to 1 upon kBt is equal to 3 exponential E nu is equal to 1 minus Ej corresponding to 1 upon kBt. So writing the value of 2990 centimeter is equal to 2990 upon 8065 electron volt, which comes out to be 0.370738 electron volt. So one can calculate Nj upon N nu corresponding to J and nu equal to 1 is equal to 3 exponential, writing the values 0.370738 minus 2 into 1.32 into 10 to the power minus 3 into 1.6 into 10 to the power minus 19 divided by 1.3807 into 10 to the power minus 23 joule per mole per degree into 1000 K is equal to 3 exponential, the value of numerator 0.368098 and that of denominator 0.086294, and calculating it, the 3 exponential 4.265642 comes out to be 214. So summarizing this module, we have understood the atoms of the diatomic molecule have been considered to be vibrating along the direction of the bond, due to which there is lengthening and shortening of the bond length. The vibration energy levels and allowed transitions between them for a diatomic molecule. We have also understood potential energy function and vibrational energy levels for diatomic molecule considering the harmonic oscillator requirement. Thank you.